All right. Good afternoon, everyone, and welcome. Today we are diving into a topic that is close to the trend of combining large language models with static analysis tools. It's about a crucial shift we believe is on the way in how we approach next generation scanner. So I hope this talk will explain what we do toward a more intelligent and faster approach. This work brings together researchers from both AI and security. My name is Hao Zong. Used to be a researcher focused on browsers, operating system, and cloud-native bug hunting and exploitation techniques, and have shoved them to the Black Hat conference in the past few years. And now I'm moving a little bit to AI's application in those areas. So the question is AI really redefined SAST? We aim to explore and analyze a different combination method based on the capabilities of each. We summarize those three ways of combining them. The first is AI enhanced design. SAST does the initial scanning, and the large model do the filter. It's quite easy to adopt it to the product and already used to some commercial productions. And the next is AI Explorer design. In this design, the large model leads exploration and reporting, while static analysis tools verify results. For example, like checking the control flow correctness. And the last is AI native design. The large model acts as a scanner itself, the whole scanner itself, nearly handling everything. It's relying heavily on the large model to drive tools and mimic both machine and human behavior. And I will attempt to review some problems inside of the design. Let's start with the AI enhancement design. The first is a case misses problem. You may could see the code snippets of official code kill rules, and you could find two interesting functions named strictly dominate and strictly post-domination. That means program point A and program point B need to have a very strong domination relationship in the control flow of the code. So this means that the initial SSD scanner acting as a front end was so aggressive in sometimes for filtering out false positives that will unintentionally miss real vulnerabilities. So no matter how advanced in the large model is in these cases, its analysis is entirely dependent on the input is received. This is a core challenge to do the trade-off between finding vulnerabilities and avoiding false alarms. Sometimes false alarms filtering even goes beyond the importance of zero-day findings. There's so much effort on this work. So for example, CodeKill had over 500 pull requests dedicated to fix the false positives. And beyond the issue of the missed issues, another significant problem is one-by-one AI reporting scanning strategy. It's really costly despite its effectiveness. While the large models analysis of individual report can be highly effective due to maybe your prompt engineering, prompt optimization, the time and the results overhead become unacceptable when scaling up to a very large number of findings. So for the reasoning, we list two different styles of using logical model here. That is chat steps and agentic steps. The chat steps is like you send a prompt to the chat box of the ChatGPT or whatever, or use the API services to get a real-time feedback. results. So the chat steps are faster using shorter context and giving step-by-step answering in real time. And the agentic steps put the plannings and tools callings and task solving all in one. It's slower but more advanced. It's working with a larger context. However, both styles face the same challenge. Each reasoning pass takes time to complete, sometimes seconds, sometimes minutes. When there are thousands of possible passes to explore, the time and the cost grows very rapidly. So it's not so effective. If we're moving on to the AI Explorer and agentic native designs, the first problem is that they cannot guarantee the completeness and coverage due to the knowledge gaps and agent readings and personality and hallucination. Actually, this kind of design still runs into cost issue. The real efficiency question comes down to this. You are asking the AI to generate one-off search style tools calling, include read, grep, such function calls, but those tools are even worse than rules. And the result, what should be a rules-based task end up getting more and more expensive through function calling in agentic system. So the fact is, SAST is naturally great at exploration the code. It's just been forced to be held back to avoid false positives. So its full power is not released. And also a rule-based system is a way more faster and more reusable. And think about it in the worst case scenario, we can just trace what agent does to explore the code and write those steps down to a new rule to achieve same goals, right? So we should first try to relax the rules, not just shift to the agentic problem solving strategies. So for better integration with larger models, we also need to consider the SAST's life cycle, include development phase and runtime phase. So the main idea of problem solving is we want to bring the most powerful larger models usage into the develop process because it's one-time effort. And at the meantime, we are expected to do the optimization to the runtime performance. Okay. So we will dive into the development phase. Please take a look at the imaging. This is the framework of Google's research launched about 2 years ago using larger model to do the optimization problem. So we could see that the larger model is the first to act as an optimizer and generate the solutions and use objective functions as a score to get the result and put every context back to the larger model to do the re-optimization. This framework is pretty easy to map into the SST's life cycle. For example, we could map the optimizer to the security research phase and the rules design phase, and map the testing and benchmarks to the objective function evaluator phase and scoring. What we need to do is make all things a closed loop. So we design a framework for the QL optimization, but with a little bit different. So first is we rely on larger model as a QL optimizer to generate the first version of QL files. And the QL would do the compilation and test on the runtime on a public test suite, and get the results and put the runtime log to the regeneration phase to the regeneration. The reason why here just look kind of a difference for adding one more edge is both QL compilation and execution phase would have terrible problem. We summarize the problem to 2 points. The first, the QL generation skills actually largely polluted in the lecture models by other languages. It was very frequently see the generated QL would combine with the Python code or the SQL code or other language identifier or grammar. In the beginning, we didn't add strict constraint on the agent behavior, so it often tend to generate a large amount of new code. As a result, due to the data pollution issue, the iteration would frequently fall into a death loop. So it cannot pass a compilation, for example. So after we think a little bit about our first insight for the limit elimination, so we quickly choose to comment on the specific code with a strict limit. By the way, we are focused on the C and C++ tensor analysis rules. There is no need to identify many framework-related things and source points. So the tent propagation is less complex than other languages. Therefore, the amount of additional code requirements is much smaller. Another thing we need to notice is the context isolation, since the control of the logs have a great effect on the evaluator's performance. That just means if you want to optimize all things in a closed loop, you do not need to feed the large model with a real code. For example, a simple case is you told the large model that case A is not included in the redundancies, so you try to prompt the agent or prompt your chatbox to tell it that you need to do the more consideration to case A, right? So he give you a selection statement, including A's 5 paths and the code line. It's meaningless, right? So it's just because the test suite you are using in this closed loop is not the same test suite for testing the same root causes of a case you want to put in the loop. This is our result. So at the first sight to solve the result, I'm very surprised by great work of the code carol teams. They really control the precision at a very high rate, nearly 100%. I'm still very shocked by we could increase the recall rate to about 3 times better. To make more people directly fill the gap, we decided to open source agent, and implementation of the agent actually makes the workflow and agentic action to get better behavior controlling. So you could directly check the code in the repo and help you have a great luck of finding more zero-day vulnerabilities. Okay, let's go to the second part, the large models in the runtime. By relaxing those rules, we obtain a much larger number of readouts with improved recall rate, right? So we have mentioned that one-by-one reasoning is unacceptable. So how do we improve on these things? To understand the problem, we need first to reflect on how human auditors think about the problem. We first know that the human auditors don't spend a very long time reasoning about every single pass. Instead, as they review more reports, they gradually summarize knowledge and become more familiar with certain code patterns or code regions, which significantly speed up the auditing process, right? So here we focus on two main questions. Where is the kind of similarity between reports enable human auditors to accelerate their review process? And what knowledge do humans gradually accumulate during auditing? After extensively auditing of the readouts, we found two main reasons for the similarity in different patterns. First, the tender analysis engine doubles passes on very small branches. As the number of the encountered branches increase, the results expand dramatically. For example, many path results may differ only slightly, but just a minor difference enough to mathematically create new distinct results. In this example, the three paths listed on the right represents different 10 choices in the propagation for the same branch in the code. And the second is after expanding the results, after expanding the rules, the number of the sink and the source point definitions are not so clear. So that also would increase the number of the points greatly due to the more relaxed point definitions. So what informations do humans actually gain from auditing those similar reports? Experienced research usually does not focus just on the flow of single variables, but pay more attention to the code context. So in other words, human actually understands the code behavior rather than the data flow. They do not simply interpret propagations or pointers like machines. For example, we show a demonstration to highlight what humans understand from code. On the left, the knowledge is very abstract, like a summary of business logic. On the right, each step is based on rules-based tender analysis without abstraction. This high-level abstraction lets us draw the same conclusions across code regions, even with different passes. This essentially reflects the difference between the context-first strategy and the flow-first principle of humans and machines. And more specifically, this process can be divided into recognizing the scope of logic, that is identifying independent code regions that understand the functionality of those code regions and the risk assessments. For example, if you ask an expert researching process vulnerability, they could very easily tell you which part of the code do the callback, right, under which conditions and have what kind of side effect. So that is a very high-level abstraction of the code region. However, code summarizations, if we want to do, we have several ways to do so. For example, we could abstract it at the function level to achieve a very high hit rate. But the downside is that the interactions between functions could be very difficult to understand due to the lack of the context. Because we lack of the function calling context. Or you could also choose a very broad level by summarizing at a full pass. But this essentially degrades to one-by-one reasoning with no benefits from summarization or catch rate. So it still seems like a trade-off between context connection and catch rate. We want to keep a good catch rate and catch hit rate, and also keep context as a complete as possible when do the summarization. So we can better understand the behavior in a faster way. We adopt a path segmentation strategy at a code blocks level, aiming to identify code sections with strong logical coherence and to abstract those with independent logic as a whole part. Our specific approach is to identify logic switch point within paths. In C and C++, a good way to detect those points is by segmenting the code at the outermost color level. The outermost color naturally located at the business logic layer with a complete stack frame context, and is also the position for coordination decisions. Yeah. This is an example. So in this code, a variable called source data is defined in the outermost function. It's then processed through a source chain, which may involve a very long sequence of function calls. After processing, the result is returned to the outermost function back at an independent functional unit. And after some propagation inside the outermost function, the code continues with the sync chain logic. The sync chain can be also involve a very long code sequence too. No matter how many variations exist in long execution paths, we care about one thing, the code, or in other words, the context. Our goal is to ensure that the summarized information from either the source chain or sync chain remain consistent, regardless of internal small changes. Therefore, the key to catching the code region lies in the context, specifically the set of the functions, function definitions involved in the code chain. This abstraction ignores the propagation. This abstraction method actually ignores the propagation flow and point definitions, which could cut down extra branches and point blood. So we can merge result from the same code and its related variable into a single catch entry. We tested this strategy and could get an incredible catch hit rate, sometimes reach 80%. Okay, next we begin, after the segmentation, we begin to the segmentation reasoning. In code reviews, humans tend to remember code patterns. This is an abstraction process. For example, in learning from historical vulnerability, a key practical experience is to trace the root causes, identify the operations that lead to the bug, and then look for the similar operations elsewhere in the code base. If we find that vulnerability-related issues are often around one key aspect, the operation. In large model analysis, abstracting and summarization by operation would get better alignment with human behavior. And different operations require different focus. For example, for the sync chain like free chains, for the source chain like free chains, you could check if the variable is cleared. And if it's a local variable or not. And for the use chain, you could check what fields are dereferenced. Those concerns are not shared and not the same across the operations, as each segment requires special attention to its specific operations. So ultimately, we aim to build a database that answers where is a segment and what does the segment contribute to bugs. This process is where humans' domain knowledge add values to the system and makes the vulnerability analysis process more manageable. When reasoning about the vulnerabilities, human would have many different corner case insights. Those insights or a specific point of the concerning attentions can help prompt the large language model for a more complete understanding of the code region. And understanding that goes beyond the large language model's standalone capabilities. So this process is a human-in-the-loop approach, gradually increase the attention point in the sort of the chain in our system. Thus, we have done the switch from the rule-based development to chain of thought development. Finally, let's take a look at the development of the soft chain items. These images show how we handle soft chain data. For example, take the COT items named trace final dereference, which is a key concerning point in use-out-free auditing. We first define a call instruction and then fill the prompt with variables directly extracted from the static analysis tools and define what large models could do in the action field. And we also do the explanation of our purpose in the process. So all the 4 key points enable us to design a better COT and complete COT items, which become a basic unit in the database. So here you can see the output of the database. We index at the function call chain level, and each COT is required to generate a corresponding check-in result. For example, the issue here focuses on the handling variables field. Since there is a tanh relationship between variable and its field, usually would cause false positives in the use-out-free check-in, making a concerning point. So we check it here. So when we revise the process, we realize that we have unintentionally transformed the functionality of the static analysis tools. The first step we take is to extract highly logically related code regions of the segment, then perform COT reasoning at the segment level to build an operation database. Beyond vulnerability matching, the operation database is also helpful for the root cause analysis and bug fixing problem. So we could do the summarization. In our approach, we could say that existing rules have a significant potential for the optimization, especially for the better recall rate. And different scenarios actually require different use of large models. We could check if we care more about the efficiency of the accuracy to use agentic way or the chat way. And different rules need different capabilities for the choice of the explore and reasoning. And humans doesn't behave like machines. So we do not force large models to do so like machines. And large model-based abstraction require focused attentions. The attention capabilities would be provided by COT's design. Thank you. We have great thanks to the collaborators, and thanks. And if you want to know more about the story behind the software chain design or the segmentation design or other technical designs, we will come to have a chat. Thank you.